Another day, another story. Dark matter is one of the greatest mysteries in modern physics and cosmology. It's a type of matter that doesn't emit, absorb, or reflect any electromagnetic radiation, which makes it invisible to current telescopes and other observational tools. However, scientists infer its existence because of its gravitational effects on visible matter, such as galaxies and galaxy clusters. Key points about dark matter. Welcome to Turbo Eminent Channel. Gravitational influence. Dark matter is thought to make up about 27% of the universe's total mass and energy. Its presence explains why galaxies rotate faster than they should, based on the visible matter they contain. Without dark matter, galaxies would fly apart due to their rotational speeds. Indirect detection. While dark matter can't be seen directly, its effects are noticeable through gravitational lensing, where light from distant objects is bent as it passes near large clumps of dark matter. WIMPs, weakly interacting massive particles. One of the leading candidates for dark matter particles are WIMPs. These hypothetical particles would interact with ordinary matter only through gravity and possibly the weak nuclear force, making them difficult to detect. Search for dark matter. Various experiments, both on Earth and in space, are attempting to detect dark matter directly. These include underground detectors designed to capture the rare interactions between dark matter particles and normal matter, and large particle accelerators like the Large Hadron Collider, which may create dark matter particles in high-energy collisions. Alternative theories. Some scientists explore alternative explanations for the observations attributed to dark matter, such as modifications to our understanding of gravity, for example, MOND or modified Newtonian dynamics. However, these theories have yet to fully explain all observations. Role in cosmic structure. Dark matter is crucial for explaining the formation and evolution of large-scale structures in the universe, such as galaxies and galaxy clusters. Its gravitational pull is believed to have helped in the clumping of matter shortly after the Big Bang, leading to the structures we see today. The discovery of dark matter. Dark matter was first hinted at in the 1930s by Swiss-American astronomer Fritz Zwicky. While studying the Coma cluster of galaxies, Zwicky noticed that the galaxies were moving much faster than they should have been based on their visible mass. According to the laws of gravity, there wasn't enough visible matter to hold these galaxies together at such high velocities. He called this unseen mass Dunkelmaterie, dark matter, theorizing that some invisible substance was providing the extra gravitational pull. Zwicky's idea was largely ignored at the time, but the notion of dark matter re-emerged in the 1970s thanks to astronomer Vera Rubin. Rubin was studying the rotation curves of galaxies and found something strange. Stars in the outer regions of galaxies were orbiting just as fast as those near the center, even though the visible matter was concentrated in the core. This should have meant that outer stars would orbit slower, just like planets farther from the Sun. Her observations were the strongest evidence yet that a massive, unseen force, dark matter, was at work. What dark matter does, though we can't see dark matter, it's believed to play a pivotal role in the formation and structure of the universe. In the early universe, shortly after the Big Bang, dark matter likely served as a scaffolding upon which galaxies formed. Without dark matter, gravity alone might not have been strong enough to pull together the particles that formed stars and galaxies. This mysterious substance is thought to hold galaxies together, preventing them from tearing apart due to their rotation. The race to find it. Scientists are on a quest to detect dark matter, which has led to a fascinating array of experiments across the globe. Here are a few major approaches. Direct detection. Scientists hope to observe dark matter particles interacting with normal matter in highly sensitive detectors. These detectors, located deep underground in places like abandoned mines, shield the experiments from cosmic rays and other background noise. The goal is to catch a WIMP or another dark matter candidate particle as it collides with a nucleus, producing a tiny detectable signal. Particle accelerators. At the Large Hadron Collider, LHC, near Geneva, physicists are smashing protons together at near light speeds to recreate conditions similar to the early universe. They hope that in these high-energy collisions, dark matter particles might briefly be created, revealing themselves through missing energy in the final results. Gravitational lensing. Observatories in space and on Earth are looking at how light from distant stars and galaxies is bent by dark matter. This effect, known as gravitational lensing, allows scientists to map out where dark matter is located, even though they can't see it. Axions. Another potential candidate for dark matter particles are axions, hypothetical particles that interact very weakly with ordinary matter. Special detectors are being developed to search for signs of axions, which could potentially be created in the Sun or even in the early universe. Theories and speculation. Dark matter is such a profound mystery that it has spawned a variety of creative hypotheses, some of which challenge the very foundations of physics. Supersymmetry. One of the most popular theories is that dark matter is composed of particles predicted by supersymmetry, a theoretical framework that suggests every known particle has a heavier superpartner. These superparticles could include dark matter candidates like neutralinos, which might be produced in particle accelerators. MOND, modified Newtonian dynamics. Some scientists propose that dark matter doesn't exist at all, and instead, our understanding of gravity needs to be revised. MOND posits that gravity behaves differently on large scales, which could account for the observed behavior of galaxies without invoking dark matter. Dark fluid. Another speculative theory suggests that dark matter and dark energy, another mysterious force driving the universe's accelerated expansion, might be manifestations of the same underlying phenomenon. This dark fluid would behave like dark matter on small scales, influencing galaxies. Why it matters. Understanding dark matter is not just an exercise in curiosity. It holds the key to some of the biggest questions in physics. How did the universe form? What is it made of? And what will its ultimate fate be? If scientists can finally unlock the secrets of dark matter, it could lead to a revolution in our understanding of the universe, just as the discovery of atoms, electromagnetism, and quantum mechanics did before. In fact, dark matter might be part of an even larger puzzle, tied to the equally enigmatic dark energy, which is accelerating the expansion of the universe. The future of dark matter research. Despite decades of research, dark matter remains elusive. But physicists remain optimistic. New experiments and collaborations, such as the upcoming Vera Rubin Observatory, will provide even more precise measurements of cosmic phenomena, potentially shedding light on this cosmic mystery. The search for dark matter is a reminder that, even with all our technological advances, the universe still holds deep secrets. What dark matter is, how it works, and how it fits into the broader picture of the cosmos will be questions that drive science for years to come. Thanks for watching. Request you to subscribe the channel.